Hello, and welcome to our exclusive technical tip series. I'm Monica Tyagi, an internal application scientist at R&D Systems Biotechne. Today, I'm excited to talk about the upstream process and how we can accelerate the clone selection process using CE analysis on our Maurice platform. Here, let's take a moment and see the evolution of our ICE family. In 1999, the early CE instruments established the early capillary electrophoresis as a high resolution protein separation technique. Research focused, single method, and limited automation. In 2012 came the ICE platform. The automated ICIF enabled robust PI and charge heterogeneity analysis, strong single method capability, and it was not an integrated platform. Moving on, in 2016 came Maurice. With the launch of Maurice, we see a major shift. Maurice was designed as a compact, automated system that could run both ICIF and CESTS on the same instrument. This moved the CE methods from specialized tools into broader analytical development workflow. At this point, Maurice started bridging early developments in QC like cases. Moving on in 2023 came the launch of our Maurice Flex. Most recently, we, with Maurice Flex, it represents full platform maturity. Maurice Flex expands capacity, flexibility, and robustness, supporting multiple cartridges and workflow while maintaining method continuity. This makes it suitable not only for the early development, but also for the late stage development, comparability, and GMP environment. Let's take a look at the simple workflow for ICIF and CESTS application. You start with inserting the cartridges, you load your bulk reagents and the samples, set up the batch using the Compass software, hit start, and then your data is ready for analysis. Why upstream analytics matter? Why decision made upstream in the biopharmaceutical productions have direct and lasting impact on downstream product quality. The biopharmaceutical production process. Now, when the biologics manufacturing, it's a stepwise interconnected process, what happens early, it cannot be fully corrected later. So, in the upstream processing, it includes cell line engineering, media and bioreactor conditions, and the production mode. These choices directly influence how the product of interest is expressed and modified. Now, the early process decision message. This is why the early process decision define downstream quality, attributes like charge variant, fragments, and overall heterogeneities are often established at this stage. Moving on to the cell culture sample and the production stage. At the cell culture stage, we are focused on optimizing growth and expression, but this is also the first opportunity to analytically monitor product attributes in the cell culture media or the harvest material. As we move to the downstream processing, it focuses on purification, separation, formulation, and the final drug substance. But purification can only remove so much, it cannot undo everything that is introduced in the upstream. Therefore, monitoring and analysis is crucial. This is where the analytics tie everything together. By analyzing cell culture medium, harvest, and purification samples, we get early insight into the product quality and can make informed process decisions before the issue propagates downstream. In that robustness upstream analytic, it enables better downstream outcome. It reduces the risk, rework, and the development timeline. The upstream processes, as we have seen earlier, they are crucial for a product development. These upstream developments, they move fast and it generates a lot of samples, often thousands every year. With the continued growth of monoclonal antibody programs, the pressure of analytics throughput is higher than ever. The challenge is that traditional methods like SDS page just can't keep it up. They're slow, hands-on, and quickly becomes a bottleneck when screening large map sets. What teams really need is a way to get reliable multi attribute data fast using minimal sample and without adding complexity. And that's where Maurice comes in. It is designed to match the pace of upstream bioprocessing and turn high sample number into actionable decision much earlier. Here and in the next few upcoming slides, I will discuss our recent application note on assessment of product quality in upstream process development using Maurice platform. In the study, a HEC293 clone producing a monoclonal human antibody was grown in a suspension with varying ratios of free L-glutamine and N-L-glutamine in the media. After the cell culture, the conditioned media was harvested for purification, and protein G map purified map samples and their corresponding cell supernatant were then analyzed on our Maurice system for both CESDS and CIF cartridge. I'll be discussing few highlights of these AppNote datasets. We did the size and purity analysis using the CESDS method, where profiles from 5 supernatants under non-reduced and reduced conditions were analyzed. Here you can see the representative profile. There's the expected peaks, namely the intact monomers, the heavy, heavy, light, the heavy, 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 light. Heavy and light were detected under the non reduced and the reduced conditions. You can see the heavy chain and the non glycosylated heavy chain and the light chain. While differences in the peak intensity between the profiles were observed under non reduced conditions, the quantification of the monomer percent peak area resulted in the comparable values, indicating that there is a variation in the L-glutamine to the glutamax ratio, which did not impact the purity of the monoclonal antibody. Although, if you can see the light chain and the heavy chain, it did not show any increase in their peak area percentage. However, a small increase in the peak percent area of non glycosylated heavy chain by 1% was observed, possibly correlating with the changes in the L-glutamine to glutamax ratio. Moving forward, we also did the charge profile analysis using the ICIF method, where the cell supernatant from the same 5 flask were also analyzed with ICIF using the native induced fluorescence detection. One of the biggest advantage of native fluorescence is its low sample volume required by virtue of being 4 times more sensitive than absorbance. This figure shows the profile of all 5 cell supernatant where heterogeneity is clearly seen with variation in the level of acidic and basic species. One of the biggest advantage of having a faster CSDS and ICIF capabilities on a single instrument is the ability to quickly analyze an array of different clones, which enables scientists to quantitate the protein of interest and make better decisions faster. In this study, an additional clone, which is labeled as clone 2, was analyzed along with the clone using the current study, which growing in a varying concentration of glutamine to glutamax. Both clones of the antibodies were analyzed using the Turbo CESDS and ICIF, and their profiles were compared. Now, here the figure shows the CESDS profile generated under non reduced and reduced conditions, respectively. Within the two clones, the results were pretty comparable. However, it is important to note the purity and charge profile between the clones can be drastically different, which in turn depends on the cell culture condition, such as the nutrients, the temperature, and the pH, and many to name. The Maurice system has already been used in analytic development in QC release, testing of over 100 commercial biotherapeutic, which make it a trusted and established solution for protein characterization. And with the introduction of Turbo CESDS, the Maurice system's capability have been extended for use in upstream analysis, making it a cost-effective solution for protein characterization that can be used seamlessly in any stage of drug development. Now let's move on to discussing our another recently published application note on integrating upstream production with downstream rapid characterization for high throughput antibody development. And I will be discussing more in few upcoming slides about this application note. A recombinant antibody production workflow, if we take a look in the left, it begins with the light chain, heavy chain expression plasmids, and it is followed by transfection and automated purification. Now, the goal here is the speed and consistency and enabling rapid generation of large number of antibody variants. A high throughput production of monoclonal antibody is necessary step for accelerating the screening and the cloning processes. But equally critical is the availability of an analytical tool that can quickly but reliably provide results that guide early selection and other informed decisions. Now, in this application note, describe a streamlined workflow that combines a high throughput production of a recombinant antibody platform with capillary electrophoresis methods on Maurice system. Over 100 of recombinant antibodies were produced on a high throughput platform, purified, and then analyzed for charge heterogeneity with image capillary electrophoresis and capillary electrophoresis for CESDS. In this study, the antibodies were expressed in HEC293 cells and purified by protein in magnetic beads. For more method details, please do refer to this application note. Now, then, these samples were further analyzed on Maurice for size and charge heterogeneity. The figures that you're seeing here, it shows a stacked profile of 8 heat-stable antibodies analyzed using CESDS under non-reduced conditions. Now, the dominant intact species samples are observed for all 8 samples. The expected variation between them as they are different antibodies. Additionally, all samples show modest level of fragmentation. The analysis of the same set of antibody under reduced condition that's on your right, it resulted in a well-resolved heavy chain, light chain peaks, along with minor peaks that are likely non-glycosylated heavy chain peaks. And minor differences in the relative migration times are observed between the samples. Here in this slide, for this, the Maurice system's onboard mixing feature was used for ICIF analysis, where samples are mixed with the reagents automatically in the system right before the analysis. Now, correctly, ICIF is a gold standard for charge heterogeneity analysis with fast method development and platform method. Additionally, this new supersonic ICIF method, which we have published recently, it leverages the existing advantage of the Maurice, including multiple voltage ramp and ability to run at a higher voltage overall. Now, this method, it further accelerates the ICIF analysis with minimal changes to the standard assays. Why I am mentioning this? Because this assay gives you a higher speed and faster results, especially when you are doing your upstream analysis with many number of clone selections. When we see the data set here on figure A, it shows a representative electropherogram of charge profile of one sample with ICIF analysis, and figure B, that is on your right, it shows a stacked charge profile of the entire set of 8 samples. The acidic and the mean species are abundant with minor basic peak, and the different PI values are observed between the samples. The next set of antibody samples that were analyzed were found to be heat labile, which is evident by the high number of the fragments detected with CESDS under the non-reduced conditions, as you can see figure on your left. Under the reduced conditions, the figure on the right, the expected low light chain and heavy chain peaks were detected for all the samples. This analysis was done using a turbo CESDS cartridge. When these heat labile samples were analyzed on ICIF, this set of heat labile samples were characterized by an abundance of acidic and basic species. As you can see, the figure on your left and figure on your right, there is an increase in the acidic peaks, which is likely attributed to the sample degradation spurred by the exposure to heat. To summarize the data we discussed so far, I want to take a moment and to highlight how combining high throughput production with integrated analytics fundamentally changes how early stage antibody development is done. First, the high throughput production platform allows to generate on the order of 100 recombinant antibodies in a single run, dramatically increasing the screening capacity without a proportional increase in time or resource. Maurice CESDS and ICIF then enables the rapid automated characterization using very low sample consumption, which is critical when material is limited in early development. The Turbo CESDS cartridge it provides the fast insight into size, purity, and thermal stability, allowing early identification of fragments, aggregates, or heat sensitive candidates. ICIF with onboard mixing, it resolves charges, heterogeneity, and detects subtle PI shifts that are often linked to post translational modification or degradation, information that is highly predictive of downstream behavior. Together, these capabilities support earlier and more confident clone selection by integrating development data directly into the upstream decision making. Overall, this integrated workflow creates a fit for purpose upstream toolkit that reduces analytical bottleneck, prioritizing manufacturable candidates earlier, and ultimately accelerates downstream process and formulation decisions. In this slide, I would like to share some key resources. We have an upcoming application note, which is on your right, on streamlined cell line development of a CD28 antibody, integrating TC Buster and AMBER technology with multi attribute characterization. And we also had a webinar where addressing the challenges of size and purity. I will highlight few of the data slides presented by the Shattuck's lab on the use of turbo CESDS for spike size analysis in antibody process purity. And for more details, please refer and scan the QR code for this webinar. In the webinar from the Shattuck's lab, they discussed the process purity analysis using the CESDS. And for the non-reduced CE sample, it was expected that all the samples would migrate as the dimer. However, the fluor glycosylation sites, they separate the heterodimer from each of the homodimer. Interestingly, the three prominent peaks were seen in the heterodimer samples. The peak 1 has a migration time identical to the BTN3A1 homodimer control that they were using. This molecule is also their least glycosylated species. Meanwhile, the peak 3 had an identical migration time to the BTN2A1 homodimer control, which is also their most glycosylated species. Between the peak 1 and peak 3, they saw another peak which is absent from the two controls. And based on these results formulated, they hypothesized that the peak 2 might be the target molecule. In addition to the homodimer controls, the purified material from cells expressing both the polypeptide chains was also used. These samples were then evaluated using the reduced CESDS application. It was expected that the disulfide bridge between the two polypeptide chains to be broken and the chains to migrate as a monomer. In the heterodimer samples, the two distinct peaks were seen with the baseline resolution between them. Each peak had an identical migration time to peak contained in their homodimer controls. Meanwhile, the homodimer control each contained one peak with a significantly different migration time from one another. The two chains have nearly identical theoretical molecular weight, but have four glycosylation site difference between them. So far for their analysis, Maurice ESDS plus cartridge was used to determine the heterodimer versus the homodimer, but throughput was lacking. So the Turbo CESDS Plus was introduced, which would provide them with 80% faster results than CESDS Plus and with up to 2,400 injections per cartridges. Here are some additional resources. The research article on the left showcases the development of supersonic ICIF method for high throughput charge variant analysis. And on the right, there's a QR code for the recent webinar on accelerating lead identification through integrated antibody development and characterization work. Just a brief summary of this integrated workflow for the antibody development and characterization. Herein, the TC Buster transposon technology enables the rapid development of the stable, high producing CHOK1 cell line expressing a CD28 monoclonal antibody. The AMBER 250 high throughput bioreactor allowed efficient testing of media and temperature effects using minimal material. The CESDS analysis for reduced and non reduced confirmed intact antibody structure with modest condition dependent size variance changes. The ICIF analysis shows media and temperature dependent shift in antibody charge variant during culture. The integrated upstream process development and multi attribute characterization enables rapid, reproducible cell culture optimization and quality assessment. Thank you for your time and for listening the Tech Tip series talk on the upstream processes and how we can accelerate the clone selection process using CE analysis on our Maurice platform.